So I'm trying to get back on that schedule where the homework quizzes are due the following Tuesday. Okay.
My question is the homework quiz due today?
Yes, I delayed week 2's homework quiz to today by 5 p.m. Yeah, so where it says on Tuesday, it should actually be today at 5 p.m. Yeah. Which page and what problem number? 393, problem 79. Yes. I'll tell you, well, actually, hold that thought, and we'll do that as soon as we start the tape rolling. Okay? Good. Yeah. So I need to put the titles up over here for today's session. I think I'm going to run back here. Are you guys recording yet? Oh, okay. I'm sorry. Today we're going to look at all 6 trig functions. And I want to start by answering a couple of questions from the homework assignments. And can you get the other 2 monitors on so that we can sort of see what's, they only have 1 monitor showing right now. All 6 trig functions. And I'm going to try to split this into 2 segments. And the second segment is we're going to try to do some applications with these things. And so the 6 trig functions we're going to be playing around here in the first segment, and I don't have in front of me what I wanted to title that particular session. Something like working with the functions. That the title on the DVD is somewhat different than that. Okay, there was a question number 79 on page 393. Question 79 on page 393. I believe it says simplify or clean up. What is it? The sine of 80 degrees times the cosecant. Is that right? Or
yes.
Of 80 degrees
Right.
also? Okay. So here's some trig stuff. It's a trig ratio right here, times another trig ratio. Now you have to know that the cosecant is the reciprocal of what? Reciprocal of sine. So we have the sine of 80 degrees, whatever that number is, and you should know this value right here, just in your brain, is going to be up near 1, isn't it? Thinking either unit circle or the function's graph. And so it should be up near 1, but slightly less than 1. Everybody comfortable with that? Okay. I'm not worried about, I don't want to punch this on the calculator because they said just work this thing out, clean this thing up. So it's actually going to be much simpler than that. The cosecant, we said, is the reciprocal of the sine. So this is actually, this ratio right here is going to be 1 over the sine of 80 degrees. Now what we have here is the sine of 80 times its reciprocal. And what happens when you take something times its reciprocal? It's always equal to 1, isn't it? So in other words, this reduces with this, and you get a value of 1. It's that simple. Uh-huh.
Can you do 87? Not same section.
Okay, number 87. Same page?
Yeah.
We'll take a quick look here. Oh, yes. This is good stuff to practice. The sine of negative 20 degrees divided by the cosine of 380 degrees, and we're going to add to it the tangent of, is this 87 on this page? Right? Is that the one you want? Okay. This I don't think I assigned, what did I? But let's use our brain on it. Let's see where it takes us. Because if you can do this, comfortably, then you're starting to feel pretty good about the material, I think. So let me help you along a little bit. There's several ways you can think about these things. Obviously, we could punch this into the calculator and get a final answer, and we could use the work we will do by hand to see if the calculator's result matches this, and we'll check that in a moment. And actually, we'll go ahead and do this other one over here in a moment as well with the calculator. But let's go ahead and think about this. Anybody want to have a suggestion? Somebody that's, say, near the back of the class, last couple rows, suggest maybe how we could think of this differently?
Negative sine of 20.
Negative sine of 20 is correct. How did you think of that?
It's an odd function.
Oh, okay. He remembers that the sine is an odd function. And so what we've learned previously in algebra and earlier here in this course is that this is the mathematical sort of understanding of what an odd function is. Okay? And notice you have the sine of negative 20 degrees, which would correspond to this. And then what that would be equivalent to then would be the negative of the sine of positive 20 degrees for that numerator. All right? Let's say you did not remember this algebra or this definition of an odd function here. How else? Anybody think of another way in the last couple rows there? People that talk the most tend to sit near the front of the class. That's why I'm picking on the folks in the back. Okay. Another way of thinking of this, if let's say you didn't remember this. Okay, let's go back to this for a second. If I'm at negative 20 degrees, that's down here. And this is the sine of that negative 20 degrees, isn't it? Right? Right there, that height. If I drew the positive 20 degree angle, it's going to sit right there. Right? And that's the sine of 20 degrees. Well, aren't those links right there the same? Except one's the opposite sign of the other one? Yeah. So if I took the negative of this value, it's going to be that value. And so there it is. Okay. Can anybody think of another way of doing this? What I'm trying to do is I'm trying to show you a variety of ways you can answer these things. Sometimes people don't like that in math. They want one way and one way only to do the math. That's not going to go very far for you. So I'm trying to show you a variety of ways of looking at it. And like I said before, this stuff fits together like a glove if you have that ability. And that's what I'm trying to help you develop. Anybody think of another way of seeing this? Something more recent that we've covered?
Well, we know that sine of 60 is pi over 3, so that means a third of pi over 3.
No, that's not quite right. What did we just cover earlier in the last couple sessions? What did we start transitioning from? We were playing with the unit circle earlier. This week, previous sessions, we've been doing function graphs, haven't we? So another way of thinking of this is draw a sketch of your sine function, right? And 20 degrees is right about here, isn't it? And so here's the sine of 20 degrees is right there, that height. But that's not actually the angle we had, is it? The angle we had given in the problem was the sine of negative 20 degrees. Where is that on this picture? It's over here to the left, isn't it? Isn't it over here? And so this is the value of that numerator up there. The sine of negative 20 degrees. I don't know if that's going to show up in the recording. It's that negative value, it's this reading right here, isn't it? And do you see how that value right there is the same as this value, except one's the opposite sign of the other? SIGN, okay? So if I took the negative of this, I would get that value. Okay? Handy ways of putting this stuff together. Now, let's try to be a little quicker about some of these others. With the cosine, we've gone around more than one whole time, haven't we? So what would be a simpler way, again, let's stick with the last back two rows. What would be a simpler way of expressing the cosine of 380? Because we know that the period of the cosine function is 360 degrees. So this is going to be identical in value to the cosine of 20 degrees. If you want a picture of that, we could use our unit circle, and I could go around to 380. See how I went all the way around and then even 20 more to get 380? And so I'm sitting right there, and the cosine is going to be this reading, isn't it? And doesn't that match the cosine of the positive 20 degrees? That length right there is the same whether you're at 380 degrees on the cosine or on just 20 degrees. Okay? You getting it? Making sense? Okay. What if we decided to think of our way into that cosine of 380 from the graph of the cosine? The graph of the cosine, you know, is this through one cycle. And let me go a little further. Okay? And this would be 300, whoops, sorry, right here finishes the cycle, doesn't it? There's 360. And this is going to be 270. This is going to be half of the cycle, isn't it, right here? And a quarter cycle right here. And it's as high as 1 and as low as -1. Gone through that. 380 is hanging out where? Right over here, isn't it? And this reminds you of stuff you did back in algebra. Is you plotted graphs, whether they be parabolas or cubics or square roots, other types of functions you studied, and the output value is the height on the graph. So it's this reading, this height right here, is that cosine of 380. Notice if you come across this graph, there's a multitude of other spots that have that same cosine reading. Okay? And so if I did a nicer looking graph, we could come back here, and this angle right here, even though my drawing's a little off scale, that's really right there, isn't it? At 20 degrees. That height matches at 20 degrees what it does out there at 380. So you can replace this with this. And then finally, what's this? Sine over cosine, same angle. We have the negative of the tangent of 20 degrees. Now added to that is this darn last thing here, the tangent of 200 degrees. This tangent of 200 degrees. Okay, one more picture. I'm going to erase some of this other stuff. So let's talk about that 200 degrees. Let's stick with unit circle for a second. Where does 200 degrees sit? Over here. 200 degrees is sitting over here, isn't it? And I've talked about the terminal side. This is the terminal side where my finger is. And that terminal side's slope is a nice way on the unit circle to think of the tangent, is the slope right there, isn't it? And doesn't that match the slope right here at 20 degrees? So this thing is tangent of 20 degrees. You add those together and you get precisely 0 for an answer. without touching a calculator. Okay. I've mentioned this early in the course, and in most of these, nowadays with your graphing calculators, you don't need to check your answers in the back of a book. You can almost always use your calculator as a backup tool to check your work. So let's take a quick look at the calculator with both of those problems we just did. And here's what I can do on this home screen. I can make sure my calculator's in degree measure, which it is. So we're in degree mode. And then on the home screen here, I'm going to look at the very first problem we did, which was the sine of 80 degrees. And I'm multiplying that times parentheses 1 divided by the sine of 80 degrees. Now you shouldn't even need your calculator on this one, right? You can see clearly they're reciprocals of one another, and so we hit enter, and you should see the final result there, 1. And that's the result we got previously. The next problem, let's take it as it's shown, sine of negative 20 degrees divided by the cosine of 380 degrees, and we're going to add to that the tangent of 200 degrees. And we get 0. Okay. All right. Let's play with all 6 trig functions now. If this made sense to people, you're starting to see how we can mix together the odd, even character of these things, and then start to be able to clean up things that look real troubling, like this last one. Okay. You need to get all 6 of those trig function graphs into your brain, and so they'll stay there in your brain. Okay. And we're probably pretty good with our sine and cosine now. I'm not even going to write them up here. What I'd like us to do, though, is let's see if we can do a pretty involved looking sine function and figure out the details on it. So let's try this. Y equals 30 sine of 3x minus, let's use degrees, minus 180 degrees. And see if without a calculator we can figure out how to draw a good pencil sketch of this. A pencil sketch without a calculator. So, right off the bat, you know that 30 is going to do what to the sine? It's going to make it 30 times whatever this ratio value is here, right? Now, how big can this sine ever get? I don't care how complex I make this in here. How big can this thing ever get? Sine can't get any bigger than 1, can it? Think back to your unit circle. Isn't this mess inside here an angle? Isn't that all an angle? So this will really help you cement this thinking. Think of that whole thing in there, I don't care what it is, as an angle. And we're talking about the sine of an angle. So that thing inside there is simply an angle, and we know that as the angle changes from our unit circle background, as the angle changes, this thing's going to rise and fall between -1 and 1 in value. So that means this y value here can never exceed 30 or never get below -30. So right off the bat, for sketching purposes, we know that we're going to have an upper bound of 30 and a lower bound of -30 on our range. So inside that bound, this thing has to oscillate. Okay, now the more interesting part, the more complex part, is inside here. I'm going to show you two ways to deal with this. One way I've already shown you the structure of it previously, but I'm going to do that first, and then I'm going to show you another way that might help you on learning this. So what I've shown you previously is to rewrite this problem, or this equation, as y over 30, and you can see this is your amplifier of multiplying by 30, which you're familiar with and seeing it up here. And inside here, where the angle sits, is I want to build the structure of this similar to the structure that I talked about in the last few sessions. And here's how I'm going to do it. I now have isolated the function, and I'm going to factor out that 3, and I'm going to be left with x minus 60 degrees. Notice the degree symbol being used. And now what I'm going to do, I'm going to go over here. Let's now get this 3 out in front, like we've seen in some previous examples, and take it down underneath there. It goes down under as a what? You can't just drop the 3 underneath here. It goes down algebraically as a reciprocal. No, it doesn't go down as a negative. It goes down as the reciprocal, 1/3. So 1/3 is sitting down underneath there, right? I think some people need some practice with fractions. How many of you need practice with fractions?
No, not me.
No, not you. Okay. Most of us need practice with fractions. So just be patient with yourself, but get the help that you need with it. Watch this. What if I had 5 times, say, 7? That's the same as 7 divided by 1/5. That's simple. That's one little simple thing, okay? Invert and multiply, or the best way to clean this up is multiply. Let's say you started here. Multiply, find the common denominator of this. This is a 7 over 1. 1/5 here, obviously. The common denominator is a 5. Multiply the numerator and denominator by 5. Look at what you get. You get 7 times 5. Okay. So in trig, this is going to be a very handy tool to think of this. This thing comes down underneath this expression as a 1/3. So this sign can be rewritten as the sign of this angle, x minus 60 degrees divided by 1/3 for your angle. That just comes down underneath this as 1/3. It's still inside here as your angle. Now, what does 1/3 do? What does this 30 do over here to the y? That did a vertical stretch. I'm repeating myself from things I've talked about previously. You know that 30 does a vertical stretch by a multiple of 30. It should make sense to you that over here, if this is your angle information, that this number hanging out underneath this x expression is going to take and horizontally, like an accordion, stretch or squeeze the graph by a multiple of 1/3. So it's going to act like squeezing an accordion and make the graph 1/3 as wide. So the period, look at the function on the original. The period is clearly 360 degrees. So the period is normally 360 degrees, but what we have going on here is by looking at this factor right here, the period of this function that we're dealing with is actually going to be 1/3. 1/3 because of the compression, the horizontal compression. It's going to make it 1/3 as wide, so the period is going to be 120 degrees. Yeah.
When you said the period is 360, when would it not be 360, or why was it 360?
4 of your 6 trig functions have a fundamental period of 360 degrees. Sine and its reciprocal, cosecant, right? Cosine and its reciprocal, secant. Okay. The two others, right? Tangent and cotangent, period of 180, fundamentally. Okay? Try to remember that. It's going to help you a lot. You'll get better grades that way too. Okay, okay, okay. So, how do we now do sketching without our calculator? How do we do sketching? We identify the period. Then what do we do? 30
times as tall.
30 times as tall, but how do we lay out our graph paper?
So 30
You find a fourth of the period. So you identify the period. This is going to be real handy throughout this course. You're going to identify the period of the function, and then you're going to take and knock it into quarters, usually. Cut it into quarters. So what we want is we want to always think of cutting the period into quarters, and so we're dealing with 1/4 of 120 degrees, so it looks like our tick marks should be occurring every 30 degrees to lay out our graph. So what I'm going to do then is I'm going to draw that with my tick marks on my graph paper at every 30 degrees. 130, 230, 330, 430. There, I finished a period. All right, I have a sine graph. Oh, now this is going to be interesting. Here's where we're going to get, this is fancier than what we've done previously. So we know we have taken our nice little sine wave. Let's see, let me go a little further here just for the fun of it. If I went another 90 degrees, no, I don't want to go that far. If I go another 60 degrees, I'm going to be at 180, right? Normally, we would have a sine wave that would be cresting here at a value of simply 1 and coming back to its node and then going on out there like that to, oops, sorry, missed it. Right? Looking like that through one 360 cycle. So there's your fundamental sine wave. So what we're doing is we're grabbing that graph, we are stretching it by a multiple of 30, and at the same time that happens, we're squeezing it in. So we create a distorted graph, and I'm going to dot it. The period's 120, and I mark these points because once I do that compression and stretch, I'm going to have it finish its cycle here. Now I want to sketch that first, lightly, for a reason. That's not a very smooth looking thing, but do you see how I use the quarter cycle points to help me? Is that looking pretty good? Yeah. Okay. Not bad on a whiteboard. Okay, one cycle. That's not the whole story though. That graph I just drew is going to be the graph of y equals 30 sine of, what would be the equation? 3x. It doesn't account for this thing. It doesn't account for that strange thing, which we played with and created this. What do you think that is?
Horizontal.
That's a horizontal shift. That is taking the graph, and which way has it shifted it? To the left or to the right? To the right. Just like your algebra background that you hopefully are familiar with. So it has kicked that distorted graph. Notice how I did the distortions first. I did the stretches and the squeezing first, and then I take that graph and then I shift it. And I'm going to shift it 60 degrees to the right. That's the reason I wanted to bubble this fundamental graph here. And now I'm going to slide that whole thing over 60 degrees to the right. And so the real graph is going to sit over here, start here. All these points are going to go 60 degrees to the right. So the final graph of this function is going to look like this. Yikes. Where am I? Where's my 180? There it is. Nope, hold it. I want it not there. Screwed that up. I got to keep my tick marks nice and even here. Where's my next tick mark? 90, 120, 60 more. No, that's, what am I doing? 30, right? 120, 150. Here's 180. This is 150 right here. That's where I want it to end. No, I'm sorry. here's the easy way to do it. This trough, right? Isn't this the trough we talked about previously? That's the bottom of it, the minimum. And so I'm going to add 60 to that. Just do the arithmetic, okay, if you're having trouble. Add 60 to that, it's going to be at 150. So this point's going to come right over to here. And then the ending point at 120, I add 60 to that, and I end up here at 180. Okay, so I had a little trouble there, and so there's the final graph. My scaling, I did some poor sketching here. My scaling should be a little wider over in here. And so then look what happens, folks. Couldn't I draw this thing back to the left from that point? That's one cycle. I could draw this back to the left, and so it's going to bottom out here and then come back up there. And it keeps on going off to the left, doesn't it? And continues off to the right as well, as a harmonic model or as an oscillator. Different words, or a sinusoid. It's just all those words get used somewhat interchangeably. When you see each other in the hallway, practice that vocabulary, and people will think you're a little strange, okay? But I'm just trying to get you to internalize the vocabulary that goes with this stuff. Okay, so there's a picture of this equations graph. You can check it on your calculator. See if you nailed it. Don't waste your time on it right now. I'm sure it's right. Okay. Finally, this is a pretty complex looking equation, isn't it? That we started with. Let's say you were turning in a report on some science project, and this is the equation you'd come up with. And you look then at the graph of this, but you want to turn in the simplest type of description of this equation. Look at this nice picture. What do you think you could give that would be equivalent to that equation as far as its behavior goes? No, that's a whole different ball game. Remember, cosecants ride on these graphs, on sinusoids. They go for a ride, so they're going to be looking weird down in here. Couldn't I just turn the sinusoid graph here upside down and not have to deal with this shifting to the right at all? Just turn that darn thing upside down? Yeah. So the equation that you can check on your calculator later is still amplified by 30, sine of, oh, and I need to make it upside down, don't I? How do I do that? I put a negative in front. Turns the sine wave upside down, amplifies it by 30, and is there any sliding to the right or left going on? Look at the picture. Do I have to slide this thing to the right or left? No. It's starting right here at a 0, heads on down, right? So, but the period is still 120, isn't it? So how do I fix the 120 period? What do I throw in here?
3x.
Just 3x. So this equation is much simpler than the original, but the graphs are identical. There's an infinite number of ways of describing any trig function. Okay, I'd like to go ahead and end this segment. Oh, before I end the segment, hang on back there. One more comment. Since we're talking about all 6 trig functions now, if we let what ride on this? Somebody mentioned it earlier. If we let cosecant, right? It takes a ride on the sine wave. So what I could do is I could lay where my zeros are, I could lay vertical asymptotes in here, and like this, and I could build this graph, which I'll try to make real dark, that and this. And the equation of that thing is going to be y equals, the easier form of it would be using this structure. It's going to be an upside down cosecant graph. So it's going to be a minus 30 cosecant of 3x is that darkened extra graph shown there, one cycle. Okay, so let's go ahead and end that segment in the interest of keeping those digital files a little shorter, and then we'll see if we can do some applications here in a second.
Visit smoothlounge.com on
Now you have to push pause down.
myspace.com/smooth.